All right, class, so this is an ALEKS topic that's called Writing the Rate Law Implied by a Simple Mechanism. And all of these problems in this topic should be essentially exactly the same as this one. And the key for this topic essentially, and what makes it a little bit simpler, is that it says, suppose also that K1 is much, much smaller than K2. What that's sort of telling us, right, this is my rate constants. It's telling us that the first step is going to be much slower than the second step. So in this mechanism, this is the slow step, and we'll talk about the implications of that as we go through the problem, but that's what this is telling us. So if the rate constant, if the value of the rate constant is much smaller than the value of the rate constant for equation 2, that's essentially telling you that the reaction rate, right, how fast that reaction is going to go, this one's going to go really slow, this one's going to go relatively really fast. So the first thing that we're supposed to do here says, write the balanced chemical equation for the overall chemical reaction. So what this is just asking us to add these two equations together. One way to think about it is you're just going to take everything from the left-hand side, bring it down, everything from the right-hand side, bring it down, and then cancel out anything that shows up on both sides. So I'm going to do the canceling out bit first, so I can see that HI shows up on both sides. So HI is my intermediate. That's what we'd call a reaction intermediate. It's produced in the first step and then it's consumed in the second step. So now I'm just sort of, writing out what's left over, and I should end up with a balanced chemical equation. So I'm going to start with H2 gas plus 2 ICl gas, and that's going to react to form I2 plus 2 HCl gas. So I forgot the gas here. So that's going to be my balanced chemical equation. When you're entering this into ALEKS, make sure you're putting in everything, in parentheses with this gas. You have your coefficients right, you have your exponents. Using these little tools here to draw your pictures properly. So this is my balanced chemical equation. We can just do a quick check. Is it balanced? 2 hydrogens, 2 hydrogens, 2 iodines, 2 iodines, 2 chlorines, 2 chlorines. So that seems good. I've canceled out my intermediate. That's another key step there. So that's going to be my overall chemical reaction. So then it says write the experimentally observable rate law for the overall chemical reaction. So for the overall chemical reaction, the rate of this reaction, the rate of both of these steps combined, is really just going to be the same as the rate for the slow step. So if you do this, run this chemical reaction where you put in H2 and 2 moles of ICl, and you observe the rate, you might do that initial rates, treatment. What you're going to end up finding is that the rate for this is going to be the concentration of H2 to the first power, and then the concentration of ICl also to the first power. And the way that I know that is because the slow step is this first step. So the rate of this slow step would be equal to R equals K1 times H2 times ICl. That's going to be the rate for this elementary reaction, right? Because this is an elementary reaction, I know that the exponents here are 1s because of the coefficients are 1s. And then since this is the slow step, the rate of this slow step, that's going to be equal to the rate of my overall chemical reaction. So for this overall chemical reaction, again, since this is the overall reaction, we cannot just use these coefficients as our exponents, but we can say, well, we know that this is the reaction mechanism, and because we know that this is the reaction mechanism, we know that this slow step, whichever step is the slow step, we know that the rate law for the slow step should be equal to the rate law for the overall reaction. That's the real key. The rate law for the overall reaction is based off of the rate law for the slow step of the reaction. The last part here, it says express the rate constant K for the overall reaction. So we're sort of looking at this value here in terms of K1 and K2. So this rate constants for those individual steps. And then if necessary, the rate constants K minus 1 and K minus 2 for the reverse of the two elementary reactions in the mechanism. So this part we're actually not going to have to worry about. This is going to be for more complicated cases. We're just worried about this simple case, the simple mechanism where the first step is a slow step. So for now, don't worry about that. We'll probably run into that later on. But in terms of this K1 and this overall K value, well, hopefully you can see that they should probably be equal to one another. So for this here, the answer is just going to be K sub 1. And again, make sure that you're using this little tool to do that subscript there, K sub 1. So that's going to be the answer here. And again, the way that I know that is just I'm going to sort of be comparing this rate law for the overall reaction to this rate law for that individual step. And then the K1 value is going to equal the K value for the overall reaction. And that's just it. All right, hope that helps.